Welcome back to another statics video. We're still looking at chapter 6 in the textbook, which is all about friction. In previous videos, we looked at static friction. And the simplest way to look at that is applying forces to an object that's either on a horizontal surface or an inclined plane. But we're going to look at a different type of friction in this video, and that is belt friction. So belts are a common way to transmit power in a mechanical system, or they can also be used as a way to slow down or retard motion. And the belt can be a rubber belt or a rope or cord or any type of flexible, in a way, a structural or mechanical member, I suppose would be a better way of describing it, a mechanical member that wraps around a cylinder or drum or pulley. And so when that belt goes around a pulley, there is a certain amount of friction. And that friction might be coming, in the case of a pulley, between the axle of the pulley and the pulley itself, or in the case of a fixed drum, the friction is between the belt and the drum itself. And that's what we're going to be looking at. We've got here a cylinder that is not a rotating pulley, but rather a fixed drum, and the belt is going to wrap around it. And so although if this was frictionless, then the tension in this belt, just like the tension in a cable, would be consistent throughout the entire length of the belt. So the tension in this part of the belt would be equal to the tension down here. But this is not a frictionless situation. There is going to be friction. When this belt wraps around this fixed drum, there is going to be friction between it and the drum, just like there was friction between the box and the plane, the either horizontal or inclined plane on which it was sitting. And so that friction force is going to affect the static equilibrium. So what's going to happen is if the direction of the belt is moving around this fixed drum in a counterclockwise direction, the tension on the belt on the lower half is going to be greater than it is up here, because there is going to be a friction force, a friction between the belt and the drum. And so the friction is going to be going in the opposite direction. So if we were to kind of take this belt and lay it out flat, we would have, going forward on the bottom side, the large tension TL, and in the opposite direction, the TS and the friction. And those two things added together would equal the large tension. So we still have equilibrium, everything is still canceling out, but because we introduce a third force of friction here, that makes these two tension forces unequal. So how do we calculate or relate these three forces together? The large tension, the small tension, and the friction force. Well, before we can get to the formula, let's talk about this variable beta. This capital beta is used to represent the angle of wrap. So what is the angle measured in radians? This has to be in radians, of the surface that the belt and the drum are in contact with each other. Whatever that angle is, that is beta. So we're going to use that variable in radians to come up with this equation here for the relationship between the large tension and the small tension. So TL is equal to TS times E. This is not another variable. This is actually a constant. This is Euler's constant. E is approximately equal to 2.718. So it's kind of like how pi is equal to 3.14. Pi is always equal to 3.14. E is always equal to 2.718. And this can be found on your calculator. You probably have a calculator button that is like e to the power of something. Or on my calculator, I have the natural log button. And if I hit the second button to use the function just above it, the e to the power of is just above it. So this e exponent and the natural log are inverse functions of each other. That's how we can get rid of one or the other in an algebraic equation by taking its inverse function. So we're taking e to the power of mu being the coefficient of friction between the belt and the drum, and beta being the angle of wrap. So multiply those things together, take e to the power of that product, multiply it by the small tension, and that will give us the large tension. So let's put this into practice. Let's look at an example problem here. 6.8 from the textbook, where we want to calculate the force that must be applied to the free end of the rope. P is what we're looking for. That's what we're going to try to solve for. To keep the weight from slipping downward for the following situation. So part A, the rope is in contact with half of the cylindrical surface. So it begins contact right here. It goes through half a rotation, or 180 degrees, and then ceases to be in direct contact with the drum. So for part A, beta is 180 degrees, but we don't want to use degrees, we want to use radians. So 180 degrees is equal to pi radians. So beta is equal to pi for part A. And so we have this 100 kilogram mass attached to the other end of the rope. If there was no friction here, we would simply have to pull down with a force equal to the weight of a 100 kilogram mass. But there is friction. Friction is going to be helping us, so we're not going to have to pull with quite as much force. So let's look at part A, where the angle of wrap, beta, is equal to pi radians. So first let's figure out what is the actual weight. The weight is equal to the mass times the acceleration due to gravity. And again, we only need to do this if we're dealing with metric units where we have been given a mass. So the mass given was 100 kilograms. So we're going to take that 100 kilograms and multiply it by 9.81 meters per second squared. 9.81 is the variable used in this textbook. I think in our physics class we only use 9.8, but according to this textbook it's 9.81, and so that gives us 981 newtons is the force. So as I said, if there was no friction here, we would have to pull with 981 newtons of force, and the two would cancel out. But there is friction here. And so what is this friction going to be equal to? The way we can determine that, it's going to be equal to the difference between these two, between P and W. And we're going to use that equation that we just introduced, that the large tension is equal to the small tension times E to the power of mu beta. Okay, so the large tension is the 981 newtons. We are going to have to pull on the other side with some force less than that. So our TL is 981 newtons, and that's going to equal the small tension times E to the power of, what was mu? Mu was given in the problem statement as 0.3. I'm going to use brackets just to emphasize that we need to find this product first and then take E to that power. So mu is 0.3, that was given, and beta is 180 degrees, but we have to convert that to radians. We cannot put 180 into this equation, it will not work. So it's pi. The relationship, of course, here is 360 degrees, one full rotation is equal to 2 pi radians. So if we cut each of those in half, half of a rotation, 180 degrees, is equal to 1 pi radian. So we've got pi radians, 0.3 coefficient of friction, and so what we want to do is we want to solve for Ts. So Ts is, actually I'm going to flip this equation around the other way. I'm going to put Ts on the left side just to give myself more room over here. Ts is going to be equal to 981 divided by e to the power of 0.3 pi. Okay, so we just plug that into our calculator to find the small tension. Okay, I plugged that into my calculator and I got 382 newtons. So if I wanted to know the friction, what is the friction force? The friction force is just going to be equal to the large tension minus the small tension. So that's just going to be equal to 981 minus 382, and that's equal to 599. So the problem wasn't really asking for this, but I just want to throw that in there. That the difference between these two forces, the reason why they are different, is because there is friction occurring here, and the belt friction is 599. So that's why we only have to pull with 382 newtons worth of force in order to keep that 981 newton weight suspended above the ground. So if we look at part B, in part B it says the rope is going to wrap all the way around, one full rotation, and then wrap around a second time. So that means that our beta, our angle of wrap, is going to be 360 degrees plus 180 degrees, which is 540 degrees. But we don't want to use degrees, we want to use radians. So that's going to be 1 pi, 2 pi, 3 pi. 3 pi radians is the beta value we're going to use. So again, our TL is equal to Ts times E to the mu beta, which means that our Ts is going to be equal to TL divided by E to the mu beta. So that's going to be equal to 981 divided by E to the power of 0.3 times 3 pi. And let's just plug that into our calculator and see what we get. I got 58.0 newtons. So that's pretty small compared to the weight over here, and that's due to all of that friction. And we increase the friction by wrapping that rope around the drum. So if we continue to wrap that rope around more and more and more, we would eventually get to the point where we wouldn't have to pull on the other end at all. Friction would be doing all of the work keeping that suspended. So that's it for this video. This is a good stopping point. We'll continue this discussion in the next video.